Hello dear students, welcome you all to the Power Hour session, and today's topic is chemistry chapter of P block. It is a very important chapter of inorganic chemistry, and there are many questions they are asking from this P block chapter. So let us continue. So let us see in P block. We are having this total 6 groups over here, and from that one by one we will be discussing about each group. Let us start from the 13th group. Okay, 13th group, that is our boron family. Okay, in this boron family we are having boron, aluminium, gallium, indium, thallium, and as you can see the electronic configuration 2s2 2p1, over here 3s2 3p1, over here 4s2 4p1, and as you move down the group you can see in case of thallium 6s2 6p1. But if you overall see this in detail, it will be 6s2 4f14 5d10 6p1. Okay, so here comes the very important question about stable oxidation number. Stable oxidation number. In this, as you can see, you can remove the 2p electron as well as the 2s electron. So boron can go up to +3. The same case in case of aluminium, gallium, indium. But in case of thallium, you can see these 6s2 electrons are very much inside. They are very close to the nucleus, so it is very difficult to remove this 6s2 pair of electrons, and that means they have become inert in nature. Inert in nature. We cannot remove them. So this pair of electrons cannot be removed. They have got inert in nature. That's why cannot be removed. And this effect is called inert pair effect. Inert pair effect. So only you can remove the 6p1 electrons. So thallium will be showing only +1 over here as the stable oxidation number. So the question they are asking over here is, what is the order of stability for +3 oxidation number? So for +3 you will be having up the group, boron will be more stable, and for +1 oxidation number we will be having down the group, thallium will be the most stable. Okay, and one more PYQ they asked from this, it was in TLI3 they asked what will be the oxidation number of thallium. So as you know, thallium can be stable in the +1 oxidation state. So the answer is thallium is in +1 oxidation state. They also asked the oxidation number of iodine. So oxidation number of iodine over here, as you can see, all the 3 iodines here will be in I3 -1 as the overall charge. So every iodine will be in -1/3 oxidation number. You can see -1/3, -1/3, -1/3. The overall charge will be -1. Okay. And also in this they can ask you what will be the structure of this I3 minus. So everybody knows we studied this about I3 minus in the chemical bonding chapter. This will be the structure of I3 minus. You can see, and neglecting the lone pairs, you can see we are getting a linear shape over here, so it will be having linear shape. Okay, so this is the important questions they ask regarding this boron family oxidation number. You can see for +3 up the group and for +1 down the group, and this was because of the inert pair effect. Okay, everybody got it? Very interesting one, which we call it as inert pair effect. So this was all about the oxidation number, and a very important question that they asked about TLI3. Hope you understood it very much. Let us continue. So now we will be first talking about extraction of boron. So for this you must be knowing that we are extracting boron, and we should be knowing the mineral ore of boron, and which is nothing but the very important one is the borax. Generally we write down the formula Na2B4O7.10H2O as the general formula. But if they are asking us what is the number of water molecule of crystallization, so for that you must know the important actual formula, and that will be Na2B4O5 OH4 times dot 8H2O. This is the actual formula from which we can get the structure as well, and from here we come to know that actually it is having how many water crystallization? 8 molecules of water of crystallization. Okay, so Na2B4O5 OH4 times. From here you can draw the structure of borax also. Structure of borax. If you see the structure of borax, what will be the structure of borax? From this formula you can write it down. 2Na plus will be standing outside. Inside there will be a ring B4O5. As you can see, this is B4O5 and OH4 times. The boron having 3 bonds will be having no charge, but boron having 4 bonds will be having -1 charge and 8H2O. So this is the structure of borax. They are asking what will be the hybridization. These two borons will be sp3 hybridized. You can say they are tetrahedral, whereas these two borons will be sp2 hybridized over here. They will be sp2 hybridized. Okay, so two borons are sp3, and you can say the shape tetrahedral, and two borons will be sp2 hybridized. You can say the shape will be trigonal planar. Okay, so this was all about the borax. Now if you heat the borax, what will happen? If you heat, you will get borax bead, a glassy bead which is used in the qualitative analysis where we have the dry test. Borax bead is used to identify the oxide which is given over there. So what is this borax bead? Let us see the formula. The borax bead formula will be NaBO2 plus B2O3. But the important part over here is nothing but this B2O3. This will be completely a glassy bead, glassy in nature, which will be reacted with the given oxide, that is the metal oxide, and you will get a characteristic color. So by this borax bit test, we are actually having identification of the metal oxide which is used in the qualitative analysis. So any metal oxide they have given, suppose CuO plus we are reacting with B2O3. Okay, so what will happen? You will get CuBO2 twice. This will be the metaborate of that, metaborate of copper. Okay, so this is the reaction which takes place. They are asking what will be formed. Metaborate of copper will be formed. So this was all about the borax bit test. They are asking what is the borax bit? NaBO2 plus B2O3, and in that important one is the B2O3. The B2O3 reacts with the metal oxides and we get metaborate of that metal. Okay, so let us see the next section. The next section is all about important compounds of boron. Important compounds of boron. What are the important compounds of boron? One by one, well, let us see what are the important compounds of boron. First compound we are talking about is the diborane. First compound we are talking about is the diborane over here, where we will be having, first of all, structure of it B2H6, that is diborane. It is a dimer of BH3. Okay, actually it is an electron deficient molecule. Why? Let us see. Why we call it as electron deficient hydride? You can call it as electron deficient hydride. Why? I will be explaining you now. So what happens in case of this B2H6? Let us see the structure. From structure you will get to know why we call it as electron deficient hydride. So what is the structure of B2H6 diborane? We are having 2 borons and 6 hydrogen over here. Every boron is having 3 valence electron. Every hydrogen is having 1 electron. So you can see there will be normal bond formation over here, which we call it as, the normal bond is called 2 center 2 electron bond. The normal bond we are talking about is normal bond 2 center 2 electron. A normal covalent bond is nothing but 2 center 2 electron. You can see there are 2 electrons involved over here and there are 2 electrons involved and 2 centers. So we call it as 2 center 2 electron bond. And after this you can see we are having a deficiency of electron. If you have a bond between these two and between these two, then these two will be separated. So we are not having that much electrons that we can have bond between these two as well as bond between these two. So there is a deficiency of electron. That's why we call it as electron deficient hydride. Okay, are you getting? So for this what will happen? A very interesting type of bond is going to be formed, where what will happen, suppose we are having this and this electrons getting involved for bond formation, but all the 3 getting involved for bond formation. So we are having 3 centers but only 2 electrons involved, and it looks like a banana. So this is a banana bond, which is nothing but 3 center 2 electron bond. 3 center 2 electron bond. The same type of banana bond you can see form over down also, where you can see there will be having these two electrons involved and these three centers, these three atoms involved in that bond. So there will be having two banana bonds. So we are having two banana bonds over here, two bonds, and normal bonds there are four bonds. So you can see because of this electron deficiency, we had to create this new type of bond which we call it as banana bond. So it is a very interesting structure, diborane. You can see B2S6, and it is famous for its banana bond. You can see banana bond is nothing but 3-center 2-electron bond. Why we call it as 3-center 2-electron bond? Because we are having 3 atoms involved and only 2 electrons in it. So we call it as 3-center 2-electron bond. Again they are asking us the preparation method. Preparation of diborane. So in preparation you have to understand we can prepare it directly by having reaction of boron trihalides with either LiLH4, and in some case you can also use NaBH4, and with this you can get the BH3 which will be getting converted to B2H6. Also one more method is there, that is nothing but hydrolysis. The hydrolysis of Mg3B2. If you are reacting with Mg3B2 with any acid or simply with water, the H2O will provide H plus or the acid will provide H plus, and you will get B2H6 over here plus MgOH twice. So you can understand that these are the methods of preparation of diborane. Okay. So this was all about the first important compound of boron, that is diborane. We saw the structure over here and also the preparation method. Now let us see the next important compound of boron, that is boron trihalides. Boron trihalides, that is BX3, where X can be fluorine, chlorine, bromine, iodine. Okay, fluorine, chlorine, bromine, iodine. So what will happen? Let us see the structure. BX3. You can see this is the boron trihalide. So we are having a trigonal planar shape over here. But as I can see, this boron has formed 3 bonds. So it is having, initially it is having 6 electrons. So its octet is incomplete. So what to do to complete its octet? What can happen over here? See, this halogen, what can they do? They can provide the electrons in the form of coordinate bond over here. So there can be a formation of coordinate bond either over by this halogen or by this or by this. There can be a coordinate bond formation between 2 already bonded atoms, and this coordinate bond between 2 already bonded atoms we call it as back bond, and the phenomena is called back bonding. So back bonding takes place over here, the phenomena of back bonding. And what will happen? Any one of them, suppose this is getting involved in coordinate bond formation. So what will happen? You can see plus charge over here minus 1. So you can see that the boron octet got completed due to this back bonding. Now you can see how many electrons does this boron have. Now you can see 2 plus 2 plus 2 plus 2. Now we are having, finally we are having 8 electrons. So octet complete over here due to back bonding. So this back bonding actually is stabilized and completed the octet of boron. So you can see either this halogen will give or this. Any one of them can give. And one more interesting thing I am telling you. By having this coordinate bond, this halogen is also maintaining its octet. You can see now also it is having 8 electrons. Just one thing has happened, this lone pair got converted into bond pair. Okay? Are you getting? Very interesting thing. Now also its octet is complete over here. Okay? By giving the lone pair, it has not lost its octet. Its octet is also complete. Only the one thing has happened is that this boron octet has also got completed over here because of this back bonding. So chemistry tells us that by giving something to anyone, you can see a very good thing chemistry tells us. By giving something to anyone, you will not get poor. Rather, you will remain as it is, and it will be a good thing for the society. So you can see we are having BX3. If X is boron, fluoride, F. If X is chlorine, it will be boron trichloride, boron tribromide, or boron triiodide. But I am asking you, if in case of this halogen being fluorine, chlorine, bromine, iodine, will it affect the back bonding? Will it affect? Yes. This is a very important point. If this boron, if you see, it is having 2p vacant orbital, and this halogen, if it is fluorine, then it will be also 2p, but if it is chlorine, it will be 3p, but if it is bromine, it will be 4p, and if iodine, it will be 5p. So you can see there is energy gap created if you go from fluorine to chlorine, chlorine to bromine, bromine to iodine. If there is back bonding between fluorine and bromine, it will be a 2p2p back bonding. If between chlorine and bromine, it will be 2p3p. If it between bromine and boron, it will be 2p4p. If between boron and iodine, it will be 2p5p. So you can see in case of BF3, it will be 2p2p back bonding. In case of BCl3, it will be 2p 3p back bonding. In case of BBr3, it will be 2p 4p back bonding. And in case of Bi3, it will be 2p 5p back bonding. 2p 5p back bonding. Okay? And as I told you, as there is energy difference created, the back bonding tendency will decrease. Back bonding tendency is inversely proportional to energy difference. So the more the energy difference, less will be the back bonding. So back bonding will be best in case of BF3. The back bonding will be best in the case of BF3 over here. BF3 will be having best back bonding. So back bonding will be more best in case of BF3, then BCl3, then BBr3, then Bi3. So this is a very important point. They are asking question about this. We will see all the questions together. So let us understand, we studied that if the back bonding tendency they are asking, BF3 will be more than, BCl3 will be more than, BBr3 will be more than Bi3. Now I am talking about one more thing which is opposite to this back bonding, and that is nothing but Lewis acid character. Lewis acid character by boron. See, what is Lewis acid character? Lewis acid, let us first understand this definition. Lewis acid means the one which accepts this lone pair, which accepts lone pair. Okay, so very interesting thing. In case of, suppose if this is BF3, what will happen? This fluorine will be having good back bonding, so this boron orbital will get filled. While in case of iodine, if this halogen is iodine, that will be having very poor back bonding, so this boron orbital will remain vacant. And then in that case, this boron can accept the lone pair. Again I am repeating myself. If in case of this BX3 is having excess fluorine, then it will be having a very good back bonding. While in case of iodine, it will be having a very back bonding, and if it is having a very back bonding, its orbital will remain vacant over here, and there is a chance of it accepting a lone pair, and in that case it will be acting as a Lewis acid over here. So very interesting thing, you came to know what is the conclusion. What is the conclusion? So the conclusion is Lewis acid character is inversely proportional to back bonding. Lewis acid character is inversely proportional to back bonding, and that's why you will be able to see that if you see the order of Lewis acid character, you will come to know that Bi3 will be having highest Lewis acid character, then BBr3, then BCl3, and at the last BF3. So this was the PYQ question. They have asked this in PYQ. And I explained you in detail, I derived everything over here, and also I talked about the back bonding. I am mentioning about back bonding also here. Back bonding, already we discussed, the tendency of back bonding is what? BF3 is more than, BCl3 is more than, BBr3 is more than Bi3. So you can see this was all about the boron trihalides. You have to understand, we already discussed that the back bonding tendency will be more in case of BF3 than BCl3 than BBr3 than Bi3, and inversely will be the Lewis acid character, as we already discussed. Okay, so they are asking question regarding this in the PYQs, you can see it. Let us see the PYQs over here. So Lewis acid character of boron trihalides is as follows. So now only we discuss that Bi3 will be having highest, and then after BBr3, BCl3 and BF3. So A option will be the answer over here, because already we discussed that Lewis acid character is inversely proportional to the back bonding tendency. Now let us see more questions they have asked. Okay, they asked what is the formula of borax. Now only we discuss, it is Na2B4O5 OH 4 times 8H2O. So this is the Na2B4O5 OH 4 times 8H2O. First option will be the answer. Generally, dear students, you know Na2B4O7.10H2O. But already we discussed that this is the formula that they initially thought, but after that they came to know that it is not having 10 water molecule of crystallization, it is having only 8 water molecule of crystallization, and we already discussed this. Because of this formula we are getting that 8 water molecule of crystallization, and so the answer will be Na2B4O5 OH 4 times 8H2. I think here there should be a bracket over here. Okay. So next, yeah, this is a very interesting question. Let us see. Now only we saw that if you are heating, this is nothing but borax. If you are heating a borax, you will get this is nothing but borax bead. This is nothing but borax bead. And this borax bead we are reacting with CuO. We already discussed that it will give a characteristic color. Like, can you see blue bead? We got it. This is nothing but metaborate of copper. Already we discussed this. So I told you at that time in these two, this important one is this B2O3. Important component is this B2O3. This B2O3 will be reacting. So this Y is nothing but Z over here. This B2O3 is reacting with the CuO and we are getting CuBO2 twice. This we already discussed now. While we were studying about the borax over here, you can see we had studied about this and I had told you that the important component is B2O3 and you can see the reaction over here that we already discussed, that was asked this in this question. So you can see we are talking about the same thing over here. Okay. So this is the same thing that we discussed. So this Y will be equal to Z. So they are asking this Z will be equal to what? Y. Okay. Because this Y is nothing but B2O3 and this B2O3 is reacting with CuO to give CuBO2 twice. So let us see another question. They are asking number of hydroxyl group attached to boron in borax. So now only I told you the formula. Na2B4O5 OH 4 times 8H2O. So you can see this 8H2O as the water molecular crystallization and this hydroxyl ions, how many they are? 4 hydroxyl ions. So the answer will be 4 over here. Next, they are asking us +1 oxidation state stability. So now only we discuss that inert pair effect. Boron, aluminium, gallium, indium, thallium. We know that down the group you can see in case of thallium we will be having this inert pair effect. So we already studied this, that +1 oxidation state will be more stable down the group. So you can see thallium will be the most stable. So if you are having this ascending order, thallium will be the most stable, then indium, then gallium, and as they have given only these 4, we are only talking about these 4, indium will be at the last one. So thallium, indium, so the answer will be thallium, indium, gallium and aluminium. Okay, sorry, aluminium. We should be writing over here aluminium, beta. Aluminium. So this will be the answer over here, thallium, indium, gallium and aluminium. You can see we already discussed thallium, indium, gallium and aluminium. So this will be the option, 4th option will be the answer over here. Okay. So let us continue. See the questions. They are asking us the tendency of BF3, BCl3 and BBr3 to behave as Lewis acid decreases in the sequence. Already we discussed this will be the back bonding, and back bonding and Lewis acid character are inversely proportional. So Lewis acid character will be this one. So the answer will be BBr3 more than BCl3 more than BF3. Second option will be the answer over here. Okay. So let us move forward now. Let us see the next section. Now we talk about boron trihalides. Now we are discussing about next compound of boron, that is nothing but we are having borazole or borazine, or we call it as inorganic benzene. See, if you are having reaction of B2H6 with NH3, then you can get ultimately this compound called B3N3H6 over here. B3N3H6. Okay? So this B3N3H6 is nothing but we are having many names. I am calling it as inorganic benzene. Why we call it as inorganic benzene? Because it is isostructural with benzene. It is isostructural with benzene. So we are calling it as inorganic benzene. So let us see the structure over here. So this is the structure. This is the structure over here. B3N3H6. That is our inorganic benzene. You can see it is looking like familiar to benzene, but benzene is an organic compound. You can see this is nothing but C6H6. C6H6. This is organic benzene. So you can see they are isostructural with each other. That's why we call this as inorganic benzene. There are three names: borazole, borazine, or inorganic benzene. If you compare them, if we are asked which one of them will be more stable, which one of them will be more stable? Of course, I will say one thing: original is original. This is original thing, and this is duplicate. Or you can go through directly the important basic thing that if there is resonance among carbon atoms, there is no energy difference over here, but the resonance over here is in between boron and nitrogen, so there will be some energy difference. In case of this, we are having charges coming over here. So there is charge separation, there is no charge separation over here. So this will be having a good resonance. This one will not be having that much good resonance. So simply you can say that stability order will be more stable. C6H6 will be more stable than B3 and 3H6. Okay, this is the question they can ask over here, or they can ask regarding the structure, the formula, the preparation of inorganic benzene. Let us continue. One more duplicate is coming over here, that is nothing but boron nitride. Boron nitride, or we call it as white graphite, and the formula is nothing but it is a BN polymer, boron nitride polymer. So this is also called white graphite because this boron BN nitride polymer is isostructural with graphite. Everybody knows graphite is nothing but polymer, 2D polymer of sp2 carbon. Okay, BN polymer, boron nitride polymer. So that's why we are calling, that's why boron nitride polymer is also called white graphite. See, this graphite, that is the carbon, this is a black one, while this boron nitride BN, this is white in color. See, this is black one and this is white. They are having same structure. The only difference is in this graphite is black and this is white. That's why we calling it as white graphite over here. So this was also PYQ asked in the question. You can see they are asking, they have asked in the PYQs. Let us see what was the PYQ asked. Yeah. So this was the PYQ question. They asked which of the following is the structure similar to graphite. So we already discussed BN. This is white graphite, boron nitride polymer, which is having same structure as that of graphite over here. Okay. Next, let us see. So this was all about the boron. Similar to boron, we can have the extraction of aluminium also by the Hall-Héroult process. As you know, we are having bauxite ore. From that we can have pure alumina, and from that pure alumina, by having this Hall-Héroult process, where first of all this alumina is melted, and to decrease the melting point we are having cryolite and fluorospar added in this alumina to lower the melting point, and then after this alumina is having electrolysis in Hall-Héroult process. From that we get aluminium. So similar to this boron family, we can have discussion about carbon family. So everybody knows carbon family. Okay, we are having carbon, silicon, germanium, ascent tin, PB lead. Here the configuration 2s to 2p2, here 3s to 3p2, here 4s to 4p2, and here 5s to 5p2, and here 6s to 6p2. But in this, if you open up, the actual configuration is 6s2, 4f14, 5d10, 6p2. So here also you can see the inner electrons, this is 6s2 electrons, will be much close to the nucleus. You can remove this 6p2 electron. This can be removed. Okay. But this pair of electrons, they have become inert in nature. This pair of electrons have become inert in nature. They cannot be removed. And this is called inert pair effect. So you can see, if you talk about oxidation over here, what will happen? Oxidation number You can see the most stable. I am writing stable one. So the most stable in the case of carbon will be plus 4, silicon plus 4, germanium plus 4, Sn plus 4, and in case of Pb it will be only plus 2. Why? Because in case of Pb you can remove only this 6p2 electrons. This is because of the inert pair effect. Or you can be asked about plus 4 oxidation number stability. Plus 4 oxidation number stability will be above the, it will be up the group, and plus 2 oxidation stability will be down the group. Okay, so this is all about the inert pair effect. In this also we are talking about catenation power. So see, what is catenation power? Catenation power is nothing but ability to form long chain. Ability to form long chain. So in this you can see what will happen. Carbon, silicon, germanium. Carbon, silicon, germanium, Sn10, Pb lead. The catenation tendency will be higher for, much higher for carbon. Down the group it will be decreasing, and Pb does not show any catenation. It do not show catenation over here. So what is catenation? It is the tendency to form long chain. You can see carbon exists in various allotropes. You have seen this graphite, diamond. They are nothing but long polymers. And similarly this silicon also exists in form of silicate, silicanes. So that is also long chain. So because of the high catenation power they are able to do it, whereas Pb cannot show catenation. Okay, they are asking question regarding this. Let us see. So they are asking in group 14 which element shows inert pair effect. So we already know it will be the lead. In 14 group we are having carbon family, carbon, silicon, germanium, Sn10, Pb lead, and this Pb will be having inert pair effect. Okay, because of this Pb exists mostly in the case of Pb plus 2. Okay, next question. Next question is, which of the following statement is correct regarding B2S6? Each boron is atom is sp3. See, if you can see every boron over here, it has found how many bonds? Everybody knows steric number. Steric number is nothing but sigma bonds plus lone pair. And if the steric number is 4, then the hybridization is sp3. So as I can see, this boron has formed how many bonds? This is 1, this is 2, this is 3, this is 4. So it has formed total 4 bonds. So it has formed 4 bonds, and everybody knows for steric number 4 the hybridization is sp3. So this is the correct statement. B2S6 is electron deficient. Yes, this is also a correct statement over here. Next, B2S6 has a banana bond. We already saw these banana bonds. There are 2 banana bonds you can see over here. These are the 2 banana bonds. And at the last we are having all of these. So the correct answer is all of these. So the correct answer is all of these. Okay, you can directly say all the statements are correct. So all of these will be the answer. Oxidation state shown by plus 13 group. So everybody discuss this 13 group, that is the boron family. This is nothing but boron family. And in boron family we saw boron, aluminium, gallium, indium, thallium. This all of them showed +3, thallium showed +1. So what are the oxidation states? They are showing +1 and +3. Okay. BOH thrice accept how many OH minus? See, boron, if you can see, BOH thrice, it is having 6 electrons. So what will happen? If one OH minus comes, it is having one vacant orbital. So this OH minus will attack and you will get BOH, OH, OH, OH and one -1 charge. And now it is having complete octet. Now it is having complete octet. As you know, this second period cannot expand the octet because they are not having d orbital. So everybody should understand this BOH thrice can accept only one OH minus over here to form BOH 4 times -1. Okay. When heated strongly, borax yield which product? So already we discussed this borax. When heated, we get borax bead, that is nothing but NaBO2 plus B2O3. NaBO2 plus B2O3. So you can see NaBO2 and B2O3 over here. So this both 1 and 2 will be the correct answer over here. Okay, we already discussed this borax bead. So let us move forward now. We were discussing about the carbon family, that is the 14th group. That is the 14th group. Let us see one by one. Now I am talking about carbon family. Everybody knows this carbon, it exists in many allotropes. And in allotropes, we know these allotropes are nothing but, dear students, allotropes are nothing but they have same chemical property. Chemical property is same beta, but different physical properties, Okay, same chemical property but different physical properties. So these allotropes are of two types, as you see in solid state also. Okay, nowadays that is a deleted chapter, but earlier we used to study allotropes. Solids are of two types, crystalline and amorphous. In this crystalline, further we used to study that we are having graphite, diamond and also the fullerenes. The most famous among the fullerenes is 360, that is nothing but Buckminster fullerene. In NCERT, they have given, see, listen, very important point. This is the purest form of carbon. On the internet, they have given different answer, but you know, in case of this NEET examination, we have to go with the NCERT. And in NCERT, they have written this line that fullerenes are the purest form of carbon. Fullerenes are the purest form of carbon. This Buckminster fullerene, if you see, it is having football shape, football or soccer ball shape, and it is having hexagonal, I can see 6-membered and 5-membered rings. Okay, and overall it is aromatic. All the rings you can see on this, they are all aromatic. So they are asking this theoretical question. Now we are discussing about graphite and diamond. Graphite is nothing but 2D sheet having van der Waals forces, and it is a polymer of sp2 carbon. You can see this will be like 3 bond formed due to this sp2 and 1 free electron. 1 free electron. Okay. While in diamond we are having 3D sheet. Okay, 3D sheet, or you can say 3D network, because 3D is not a sheet, it will be a network. 3D network, polymer. Diamond will be a 3D network polymer, and the hybridization will be sp3 carbon. Okay, because of this free electron only, you can see this carbon is having good conductivity in case of graphite. So that's why graphite is a conductor. If you compare between graphite and diamond, graphite is conductor only because of this 1 free electron. Okay, and the most important thing we are talking about is stability in these two. We are having the comparison of stability between this graphite and diamond. If you see, a very interesting fact comes between these two, that graphite is more thermodynamically stable than diamond. Graphite is more thermodynamically stable than diamond, because in nature, if you see, if you give the heat, this equilibrium between this graphite and diamond, if you see, this is a process going on inside the earth crust. If you provide heat, what will happen? This equilibrium will be established towards, it will move towards the graphite. So this shows that thermodynamical stability is more in case of graphite as compared to diamond. Okay, so this was the question asked. Let us see. Most stable allotrope of carbon thermodynamically is. So as I discussed now, that graphite is the most stable thermodynamically allotrope of carbon. Also, questions related to allotropy. Allotropy is due to difference in the number of atoms in the molecule. No, difference in the arrangement of atoms in the molecule crystal, difference in chemical properties. See, already I told you chemical properties will be same. This is also incorrect. The only option is the B option, difference in the arrangement of atoms in the molecule crystal. That's why physical property will be different. Physical property will be different over here, but the chemical property will be same. So the answer will be B option. In diamond, carbon will be, now only we discussed that the carbon will be sp3 hybridized over here. So the correct answer will be A option. Now graphite has, so we already discussed 2D sheet structure, van der Waals forces between layers, sp2 hybridized carbon linked with other 3 carbon atoms in hexagonal. Yes, this is also correct statement. In solid state, we used to study about this HCP, hexagonal close packing, which is taking place in this graphite. So all the options will be correct. So the answer will be all of these. So this was all about the P block section we covered over here. We covered the boron family and carbon family. See, we are having a limited time over here. In this we can discuss many things, but quality is more important. So we studied about them, and then after that we discuss all the PYQs that they ask in NEET examination. Hopefully you enjoyed this session. So thank you so much for joining. Let us meet in the next power hour session. Thank you so much.